Hey, it's Executive Editor Stephen Lacey. If you're hearing this on the Carbon Copy, you know me as the host. If you're hearing this on Catalyst, you know me as the voice that is sometimes confused with shale. And I've got some news, so don't fast forward. Postscript Media, the company that I co-founded, that produces this podcast in collaboration with Canary Media, is soon going to be rebranding as Latitude Media. It will be a B2B news and analysis outfit covering the new frontiers of climate tech. We're going to still be partnering closely with Canary Media on the Carbon Copy and Catalyst podcasts, so rest assured these pods will continue, but we will be launching a new B2B news site covering business and tech trends across advanced grid tech, artificial intelligence, carbon removal, long-duration storage, and more. We've been hiring reporters and analysts, and you can go to latitudemedia.com to find out more when we launch in October. And that brings us quickly to two events coming up in October, Transition AI New York and Canary Live Bay Area. Transition AI is hosted by our team at Latitude Media. It's the premier event charting how artificial intelligence will shape utilities, renewables and storage developers, energy traders, and EV charging integrators. Transition AI New York is a one-day conference and workshop. It's in Manhattan. It'll be on October 19th, so mark your calendar. It'll feature top experts from Microsoft, GE Digital, AES, National Grid, Oracle, and a wide range of founders, executives, and academics who are building AI strategies right now. Plus, we're going to have a detailed market map of the industry that we've been working on, and our podcast listeners get 10% off if you go to transition-ai.com or follow the link in the show notes. You can get your ticket and use the code PSPODS10 on checkout. Transition AI New York. We'll see you October 19th. And for the folks in the Bay Area, our partners at Canary Media are putting together a live event on October 3rd. It's going to feature a roster of top journalists and experts that are handpicked by the Canary Media editorial team. It's at Freight and Salvage in Berkeley. And they're going to bring those experts together to talk about all things energy transition, Inflation Reduction Act implementation, and tech innovation. We recently played this popular conversation between futurist Ramez Nam and journalist David Roberts. That was recorded from Canary Live Seattle. So we got a great response from that episode. And if you liked it and you want to network and you're in the Bay Area, get your tickets for Canary Live Bay Area. Again, it's on October 3rd in Berkeley. We've got a link in the show notes. And now, on to the episode.
From the studios of Postscript Media and Canary Media.
I'm Shail Khan, and this is Catalyst.
And a lot of climate scientists are sort of saying, yeah, sure, this might have had a tiny effect on global temperature, but it's unlikely to have had any contribution to any parts of the system, right? It hasn't contributed to heat waves this summer. That might be very well true. But then if that is true, that does tell us a lot about what would be a permissible geoengineering experiment.
You know that thing where you change the rules in the shipping industry in order to clean up the air, and in the process, you sort of accidentally stop a decades-long experiment in geoengineering? You know that thing.
Let's face it, environmental news is often very depressing. That's why we focus on solutions on this podcast. But still, the climate crisis looms large. Rising temperatures, mounting pollution, environmental degradation, they're all warping the planet. And for a lot of species, including us, things don't always look so great. But the story doesn't end there. Every Friday, Living Planet, a show from Deutsche Welle, takes you behind the headlines to figure out what's happening and how we'll get through it. It'll also help you make better choices for a healthy planet and find space to reconnect with the beauty and wonder of the world around us. You can find Living Planet wherever you get your podcasts.
I'm Shail Khan. I invest in revolutionary climate technologies at Energy Impact Partners. Welcome. So my colleague at EIP, Michael Campos, put it best. He said, oops, we stopped geoengineering. And really, that's basically true. So we've been spitting sulfur dioxide into the atmosphere for centuries because of emissions from shipping. And it turns out that those sulfur aerosols cause clouds to be more reflective, which is exactly what we're talking about doing when we consider deliberate geoengineering. But then we stopped. In an effort to reduce air pollution, the International Maritime Organization, or the IMO, instituted new regulations in 2020 on high sulfur fuel that significantly reduced the amount of these emissions. So, what happened? How big a deal is it? What does it tell us about the future of doing the opposite? In other words, intentionally adding sulfur aerosols to the atmosphere in order to cool the planet? We're back in geoengineering land. And so I brought back my geoengineering guy, Dan Visioni. That's right, I have a guy for this. Dan is a climate scientist and an assistant professor at Cornell University's Department of Earth and Atmospheric Sciences. Here's Dan. Dan, welcome back.
Thank you. Thank you for having me again.
Let's do an update on geoengineering, and in particular, talk about this sort of accidental experiment that we have run in the world, wherein we sort of were geoengineering and then sort of stopped. Let's run through that in a little bit more detail, starting with just walk me through prior to these new regulations, which we'll talk about, that the International Maritime Organization created. What was the type of emissions that we were producing in shipping that was relevant to, impacting climate change, and how much of it were we producing?
Mm-hmm. Yeah, so we emit, normally humanity emits a lot of sulfate, mostly through the burning of fossil fuels. And for a long time, one of the main culprit of this burning was shipping fuels, so emissions from ships. And for a long time, they had the fuel that was used was not particularly clean. And up until the 70s, there was a very robust theory suggesting that pollution would actually make clouds brighter, especially in some regions. And one of the main regions where this could happen, it was always suggested to be the North Atlantic corridor. So where most of the shipping happened for a long time, but also one of the areas that was more susceptible to actually being affected by this effect. Essentially, the theory suggests, and actually it's a pretty robust result, that whenever you have, so normally you would have cloud just from cloud droplet condensing, water vapor condensing. If you have more cloud nuclei, so particles that allow these coagulation, this condensation to happen, the more nuclei you have, the more this water vapor that condenses is distributed across more nuclei, and so you have smaller water droplets. And the optical depth, so basically how much clouds can reflect solar radiation, depends inversely on the surface available, so on the size of these particles. So essentially, tinier cloud droplets, brighter clouds that can reflect more sunlight. This was suggested in the 70s, and proven in the lab a lot. The main challenge of actually observing this in the real world was that clouds are already an incredibly variable piece of the climate system. They're not that easy to observe because they happen for a lot of meteorological reasons as well. So it's hard to figure out whether a cloud is there for one reason as opposed to the other. One of the locations where this is probably in a way easier to detect would be the North Atlantic, again, because there's no mountain, so it's not like clouds can be formed just from orographic waves. There are sort of prevailing wind. There's many reasons why. But on the other hand, the North Atlantic is huge and there isn't anything else but ships, so it's very hard to detect for other reasons. But there was a very strong suggestion in the literature for decades about the fact that shipping was making clouds brighter. Burning from shipping was making clouds brighter, especially over the North Atlantic and in general over the oceans. Again, all of the proof about this was in many ways very well. There were a lot of methods to try to detect this, but the essential problem was that a counterfactual was lacking. Anytime you would see a bright cloud, it was hard to determine how much less bright it would have been if it weren't for the ship, right? And so suddenly there was this natural experiment in a way. Well, not natural because it was man-made, a decision from humans. Since the main thing that sulfate does is not brightening cloud, but is actually being very bad for health, right? Especially when it comes very close to the surface, all of this particulate doesn't only produces more cloud, but also ends up in the air that we breathe. And especially when it's very tiny because it's a byproduct of combustion, it can get into our lungs very easily. So it was just, in a way, natural for the IMO to eventually ask all of the shipping world to cut back on the amount of sulfate in the fuel, which is exactly what happened in 2020.
Okay, so we'll talk about what the IMO did, I guess, in just a moment. But first, to level set again. Okay, so it was always sort of theorized, and it seemed likely that if we emitted a bunch of sulfate into the atmosphere, it would brighten clouds. Those clouds would reflect more sunlight. That would have a cooling effect on the atmosphere. And that was particularly true. It would be particularly susceptible over the North Atlantic, which just coincidentally happens to be a major shipping corridor. Is that right? And can you maybe explain a little bit more, like why the North Atlantic corridor is particularly good for this effect?
Right. Okay. So in general, the assumption that pollution would brighten clouds sort of applies everywhere in the world. The main problem, though, is over land. It's very hard. There are so many things changing all at once that sometimes it's very hard to determine why is a cloud forming or not. There's orography, so there are mountains, there are hills, there's many byproducts of pollution. So it's very hard to actually figure out, is that cloud brighter or not? This effect is sort of more evident over the oceans, just because there's no orography, there's just waves. And there's the water vapor coming up from the oceans. And of course, the main corridor in which a lot of the shipping happened, especially in the last 50, 60 years, was the North Atlantic one. So a combination of the oceans are flat, and so there are many less ways in which clouds can form. There's a lot of ships in the North Atlantic, plus some sort of more complicated reason why the North Atlantic produces produces less clouds normally, and so these clouds can be more affected, right? So this effect, this is very, very complicated, I understand, but so this effect of cloud brightening from aerosol can only happen up to a point. You cannot make these tiny droplets incredibly small. So if there's already a lot of clouds and those clouds are already small, they are less susceptible to actually being affected by the aerosol. The ones in the North Atlantic, the clouds in the North Atlantic, tended to be the perfect target where these aerosols would reduce the size, and there were a lot of them. There were a lot of shipping tracks.
Okay, so it's a combination of what we believe would be a larger effect if you were to release the same amount of aerosol over the North Atlantic versus over land, larger effect and easier to measure for similar reasons, basically.
Yes, and the other big difference between land and the ocean is that the oceans themselves, without clouds, have a very low albedo. So they absorb a lot of solar radiation, much more than land. And so anything that increases albedo over the ocean, such as clouds, is going to have a bigger impact in terms of global temperatures and radiative forcing than things happening over land.
I'm also interested to do a quick comparison. I think the last time you were on here, we talked about the impact of volcanoes, which are another sort of like major sudden effect we've seen multiple times in history, where a large volcano spews a bunch of sulfur into the atmosphere as well, and we've seen cooling effects from that. Are those the same aerosols getting released more or less, or the same effective molecules coming from a volcano as we saw from shipping emissions, or is it something different?
They are sort of the same, except that their impact is completely different. So for volcanoes, just to remind people, the main thing is that volcanoes often emit sulfate also near to the surface. There are effusive volcanoes. But once in a while, there's these explosive volcanic eruptions that bring a lot of sulfate all the way to the stratosphere, where there's normally neither clouds nor sulfate, just a little bit. And there aren't any removal mechanisms for these aerosols. So these aerosols are free to float around for sort of 1 year, 1 year and a half. They grow more because they have more time to condensate stuff around themselves, just because there's no removal mechanisms. And so they tend to have a pretty strong forcing effect just because of the direct reflection of sunlight from the aerosols, way before the sunlight can get closer to the surface, what we call the troposphere. The sulfate is the same that gets produced by the byproducts of fuel combustion when it comes to shipping tracks, except in this case, the aerosols themselves, their lifetime is pretty tiny because they get emitted very close to the surface, and so they immediately fall down. So the direct, in this case, is not as much a direct effect, that is much, much smaller, but is the indirect effect. So the what we call the aerosol cloud interaction effect. So the fact that these aerosols, they act as cloud nuclei, and they increase the reflectivity from clouds, which are so much more effective at reflecting solar radiation. You can imagine this just by seeing, you can see clouds, right? Because they affect the visible part of the solar spectrum. Whereas aerosols are much tinier. They are pretty effective at reflecting, but not as much as clouds are. So they are the same thing, but by happening in different parts of the atmosphere, they produce very different effects. And we can see these just based on the numbers, right? So Pinatubo, one of the biggest eruptions of the 20th century, Pinatubo happened in 1991. It released anywhere between 10 and 20 teragrams. That's megatons. So that's a million of tons of sulfate in the stratosphere. We call that a big number, but it just released it once, and it had an effect for a couple of years, and it had a pretty big measurable effect in terms of cooling. On the other hand, humans emit 10 times as much that every year. Well, now we're cleaning up our acts a little bit, we're cleaning up our emissions, but in the 90s, while Pinatubo happened, the world just naturally, from anthropogenic sources, it emitted over 120 teragrams, so 120 megatons of sulfate. But that sulfate was so close to the surface that its radiative effect, the cooling capability, was much, much smaller. Right now, the IPCC estimates that aerosol emissions from the surface have probably hidden a small fraction of the overall global warming, probably 0.3 to 0.4 Celsius. Whereas Pinatubo itself, just by that outburst of that tiny fraction of sulfate compared to the one we emit, probably cooled the planet by the same amount. So 0.3 Celsius.
Okay, so now let's go back to shipping then. So what are the regulations that the IMO put in place in 2020? And then we could talk about what impact we've been able to measure since then.
Mm-hmm. Yeah, so as I said before, our main worry with sulfate when it gets emitted so close to the surface is that we end up breathing it. Normally, it also happens very close. Those emissions also happen very close to where people live. So it's sort of a big problem. So it's only natural that as soon as there are things that allow us to clean up our air, people want to do that, and regulations end up being in place, right? The Clean Air Act from Reagan was just about that, and it had a massive impact. So the IMO did sort of the same thing. There have been plenty of reports saying how big of an impact on air quality over the Northern Hemisphere this could have if there was this cleanup of shipping emissions. And so they finally put this regulation in place that prescribed that either the content of sulfate in fuels had to go down as a mass fraction from 3.5 to 0.5, so really 7 times less sulfate in fuels from one year to the other, or that ships had to have scrubbers capable of cleaning up this SO2, this sulfate, before it reached the atmosphere. It happened from the first day of 2020. There was indeed this new regulation. Everybody seems to be. It's also very hard to determine whether actually everybody respected it. But the funny thing is that we can see it indirectly by the fact that we have observed that clouds have changed out of that. The estimate for now is that there was probably a reduction of around 7 to 8 megatons of sulfate emitted less from shipping. That's 10% of the overall emissions right now of sulfate from the whole world from anthropogenic emissions. And indeed, in the last few years, there have been already a few papers sort of analyzing through satellites, images, and machine learning, a lot of other stuff, how much have clouds changed. And it looks like there's a pretty robust sign that was exactly the same that was sort of predicted before these regulations went in place of how much this has reduced cloud coverage.
And can we go a step further then at this point and say how much that has increased global mean temperature?
Yes and no, in the sense that, so So what scientists normally do is they don't immediately go into talking about global mean temperature for a lot of reasons. But the first thing that we can see is what we call radiative forcing, right? So basically, now we can measure it from satellites. So there's a few satellites. There's a very famous NASA one series that has been on now for a while that can basically measure the energy fluxes in and out of the world, in and out of our planet. So our energy fluxes coming in is just the sun, but the energy fluxing coming out are a bit of shortwave radiation, so a bit of solar radiation that gets reflected, but also the planetary radiation, the infrared radiation that gets emitted by the planet. And normally, if the planet was in perfect equilibrium year by year or over longer timescale, over a decade, there would be a perfect balance. Exactly as much energy comes in, exactly as much energy comes out. Otherwise, the planet would just warm. What's happening right now is that the planet is warming, mostly because this budget is not perfectly balanced, because the greenhouse gases trap a bit more solar radiation. And Ceres has been indeed capable of measuring how much of this equilibrium, of this what we call Earth energy imbalance, has happened over at least the last 20 years. And that's roughly sitting at around 1.2 watt per square meter. So that's an energy flux of it doesn't sound like a lot, but in terms of that's as much energy every square meter remains into the system and doesn't get emitted back. That's quite a lot. And so temperature eventually responds to these changes in forcing, but not perfectly, because a lot of the energy gets actually stored in the oceans. So the response of temperature, it might not be as linear, and is also the temperature responds linearly to increase in CO2 concentration, but not to forcing, not directly. And on top of all of these, there's also year-to-year variability. So with all that said, there have been a few estimates based on some very coarse global modeling, in a sense, not even going into a climate model, but just knowing the Earth sensitivity. And in general, the observations were that, the observations and theory sort of agreed on the fact that probably globally, this change in shipping regulations has contributed 0.1 watt per square meter globally. So that's 10% of the Earth energy imbalance going in the same direction of the Earth's energy imbalance, right? Because it has allowed more solar radiation to reach the oceans that then store that heat. There's a few coarse estimates that, just based on Earth sensitivity, suggest that there's probably a tenth of a degree overall of increased warming. So if you, again, big or small, it depends how you're looking at it. But one way to put it is that it's definitely smaller than the year-by-year variability in our climate system, right? Just something like the El Nino system, what we call ENSO, normally drives a big part of the year-to-year variability in the global mean temperature, because it directs how much of the colder water in the Southern Ocean gets in the oceans get mixed up. And so year by year, it does affect a lot how much the global mean temperature of the planet warms or doesn't warm. And so these 0.05 Celsius might look sort of not big, but not even small if we think about where we are in terms of the Paris Agreement and all of that. But on the other hand, it is not so fundamentally easy to detect something like this. Right, I guess that's the main problem. And that's also where a lot of my research is focused on this year, is sort of exactly try to answer this question. But also, I think that aside from putting an actual precise numbers to this, it really speaks to us to how complicated it is, and how the biggest challenges that right now we're facing, many challenges, but the one that interests me the most is really around this issue of detecting and attributing changes to our climate system due to one specific activity or not.
I mean, it's also just one of these examples of one of these unforeseen trade-offs, right? So, for all the right reasons, the IMO instituted regulations to demand low sulfur marine fuels for local air quality reasons, or for direct air quality reasons. it sounds like what you're saying is that maybe unintended consequence of that is at least a globally significant impact on radiative forcing. Maybe not the biggest, but measurable on a global scale at a minimum. And so that's obviously a trade-off. Might be worth it, but it's a trade-off. I guess I'm wondering, as you said, sort of the overall impact on sulfate emissions from these regulations was maybe a reduction of 10% or so. So theoretically, you could imagine then we have 90% more sulfate emissions that we probably should get rid of because of air quality. And so maybe the ultimate impact could be 10x. Now, I know you also said that this seems to be the one with where the sulfate emissions were most likely to create the biggest impact because it's over the Atlantic corridor. So do we have any sense of, what the overall trajectory of sulfate emission, of anthropogenic sulfate emissions might look like and the degree to which that might have an even larger version of this effect over time?
Yeah, I mean, absolutely. So if another thing that I feel there's a lot of confusion on, sometimes when people talk about net zero or what would happen if suddenly we completely stop all emissions. And the main answer to that is that we know that if tomorrow morning there were no more anthropogenic emission of anything at all in the world, the main impact that we would see in the first decade, it would be a warming, because this aerosol effect that is masking part of the warming would be the first one to go away. Of course, over the long time, we would see other effects, the methane lifetime being smaller, and then overall CO2 would trump over everything over a century. But that would be the first effect. We know this is exactly what would happen. And for what you said about the trade-off, I would say that this clearly feels like a point where there was a large part of the scientific community that was a non-zero part of the scientific community that was interested about this issue with shipping. But if you read the literature, I've been reading a lot of that in the last few months, it was taken for granted that it was obviously going to have a forcing effect. But the consequent step of asking, well, how does this square with Paris Agreement commitments or in general with our current concerns about global warming wasn't there. In a way, it was considered such a no-brainer trade-off that probably wasn't worth it. But also, on the other hand, I do feel like there's a paradigm shift around these issues with, again, detecting a specific change that is just now coming up, right? And so, for instance, and I think, so the numbers I mentioned before about global changes, they're absolutely valid. I don't expect our estimate that we're going to have in the near future to be that different. But on the other hand, that we're talking about global numbers. What those kind of estimates haven't touched on is what would be the more regional effects, right? Because in order to have a 0.1 forcing over the whole world, it means that over the regions where these changes happen, this forcing has probably been much higher, roughly 10 times higher, like 1 watt per square meter. And I feel like the question that now I'm definitely very interested in, and I hope many more people in the scientific community should be interested in, is, well, what regional effects and with what transboundary effects? So if we change the heat coming in the North Atlantic, how is that going to affect the rest of the system, right? For instance, I've read a lot about this in the last year as well, of people speculating. If we look at 2023, if we look at this last summer, there have been a lot of people saying, well, look at the massive heat waves over Canada or the massive fires. Look at this big ENSO, this big El Nino coming up. Look at how hot the surface temperature of the sea have been or the Mediterranean. Why? Can this just be explained by a mix of natural variability plus the long-term warming, or was there something else? Some people dismissed it. Some people, I think, overplayed. I feel like this is really an area where we should be researching a lot more. And I do think that there is, in a way, a bit of resistance just from the scientific community. I'm not claiming anybody's hiding anything, but just in terms of how we think of our effects on the climate system. The CO2 one is the one that we're most worried about, but in a way, it's also the quote unquote easiest to understand, just because when CO2, we put it in the air, it mixes well, it has an effect that is sort of global, cumulatively. But when we think about something more regional, that can have maybe big effects over a smaller area, we should really, and then that brings us to the question of how should we be thinking about that, right? Again, as you said, exactly as you said, so there was this regulation, but nobody at the IMO mentioned or thought, well, what effect is this going to have on North Atlantic sea surface temperature, and is that going to contribute to heat waves? I do not claim that that's not a good reason to have actually had this regulation, but in a way, it's a discussion that it's worth having and that we should be having more.
Let's talk about the reverse of this. So I think there's two things to talk about here, right? One is what is the impact of the IMO regulations and future decisions that we might make around air pollution reduction. But obviously the other thing here is we've talked before, you and I, about deliberate geoengineering and the concept that maybe things are going to get bad enough that we want to consider purposefully putting sulfur aerosols into the stratosphere in order to create cloud brightening, in order to reduce radiative forcing. And one of the challenges with that whole field, obviously, is it's wrought with questions and risks and all sorts of challenges that make it difficult to do a whole lot of testing, even. So in some ways, it feels like what we did here is we sort of accidentally did a reverse test, which is, turns out we were already doing a version of it. We stopped doing that, and then we can measure the impacts. Is there anything that we can learn from the IMO regulations and the sort of, before and after effects that might tell us about efficacy or cost or anything like that, or side effects to do with the opposite, purposefully putting sulfur aerosols in the atmosphere or in the stratosphere?
Yes and no. So I think that there's a lot of things that we can learn. They're not necessarily about these exact effect playing out, but I think there's a lot that we can learn, and I'll explain a bit better. So there's the main thing that you would assume that if we were already thinking a bit more seriously about this sort of climate intervention, so these actual on-purpose interventions in the climate, that we, as scientific community, the whole world would have said, okay, this is happening. Let's make sure that we can detect it. What do we need? Let's actually put a lot more focus into it than what there's been, right? So, because the issue is always going to be, whatever we do, both in a way in terms of global warming, climate intervention, regulations, anything, is that we only have one planet. Finding the counterfactual, so figuring out what would have happened if we hadn't done this, or if we do this, it's always going to be hard, and it's always going to require us to, in a way, trust in the climate models that we need to use to build these counterfactuals. Now, for climate change, so it's in a way gotten so much easier. We've known about climate change even before we could detect the signal, or before we had the climate models to tell us. But now it's so obvious that, in a way, it is pretty easy to attribute the warming just to the anthropogenic emissions of greenhouse gases. For everything else, though, we're still at the point where we should be thinking a lot more about what it means to detect these kind of changes, both intentional or non-intentional. So if we, as the whole planet, had been, in a way, maybe 10 years from now, in a maybe more serious trajectory of actually thinking about climate intervention or geoengineering, it is potentially we could have done more into making sure that we were observing better the whole system, and making some prediction and figuring out how our prediction were going to play out in what actually happened. We're still doing it. We can still, that's a lot of what in my group we're doing right now, which is trying to figure out, well, okay, but how do we build this counterfactual? What does it tell us? How do we think about it in terms of variability? So that's one thing. The other thing is that right now, so in the last year, there's been a lot of advances in bringing the conversation around geoengineering to a more global public, right? There's been plenty of reports from very influential places. The White House has had a report, the OSTP, the Office of Science, Technology and Policy, has had a report about it. The European Commission, the United Nations Environmental Program. There's been plenty of reports saying, hey, there is this thing, it should be on our radar. What do we do about it? And a lot of them are always very vague about what should we do with experiments, right? How do we figure this out in the real world? And because one of the main problem is, well, how do we make sure that we have an experiment that can teach us something, but also is not too dangerous or that doesn't have consequences we don't know about? And I think, and I'm really trying to explore this a lot more, that this example of the shipping regulation should really be can really tell us a lot about this, right? So, because we are claiming that this effect is maybe there, but it's small, and a lot of climate scientists are sort of saying already, in a way, before having done the research, because maybe that's their best guess, that, well, yeah, sure, this might have had a tiny effect on global temperature, but it's unlikely to have had any contribution to any parts of the system, right? It hasn't contributed to heat waves this summer. That might be very well true. But then if that is true, that does tell us a lot about what would be a permissible geoengineering experiment from which we could learn things like we learned. We had another proof of the fact that this effect of brightening clouds was actually true. But also, if we're claiming that these did not have any real attributable effect, then that does tell us something about, well, there is a category of permitted experiment that can inform our modeling and our knowledge, but that is also, we can safely say this does not have any long-term effects. And I feel like, this is probably why people are sort of reticent to talk about this too much, but I think that actually the way we should be really hammering on much more, which is, well, if now we're at the point where we can attribute these changes and say, look, it's there, it's a signal, but it just gets submerged in the variability of the actual system, that can tell us something about what is the size of a sort of large-scale experiment that might tell us something about geoengineering, but it is also way below the threshold, which is not safe anymore.
So I guess just to wrap up then, it's been, I don't know, a year and a half, maybe something like that, since the last time we talked about the state of geoengineering. Separate and apart from the IMO regulations, the impacts there, what has changed, if anything, in the past year and a half? Have we progressed on the science? Are there more experiments, like real world outdoor experiments, scheduled, or is the field in a state of stagnation because of inability to agree upon, whether or not we should do it in the first place?
Well, that depends. Again, it's another one of those answers that's going to depend a lot on how would you decide to determine success or not. So, no, there haven't been any large-scale experiments. Australia has claimed they're doing something very local to preserve the coral reefs, but that's not something you would consider large scale or even at a measurable scale. They're not even calling it an experiment, just as an adaptation measure. So there haven't been any proposals of any kind of global experiments. On the other hand, as I was saying, because I think that that's not the main hurdle right now. I don't think that what determines whether this field and this discussion is successful or not is going to depend on how soon do we have a global experiment. I still think that the best way to measure this is, are we getting people to think about it in the right way, and not just people, but international organizations and states as well. Because really, whatever happens, we're not going to geoengineer the planet in the next decade. There's no appetite. It's extremely unlikely. But also, we do still have and I'm happy about this in the sense that I do think that we still need to be thinking a lot more about this. And if we want this kind of intervention to be non-approached in an hostile way by a lot of people in a lot of states, we need to actually be out there and talk about this a lot more and be sure that we can reassure people and that we can have a robust science behind it. And so from my point of view, the main thing that we need to do, and what, again, I feel like it's really happening, is that we need to have this conversation about whether we should be thinking more about this at a global level and an international level. And so again, the European Commission, the White House, the United Nations Environmental Program, UNESCO, there have been tons of reports. Do these reports say anything new? No, they don't. But the fact that all of these organizations are having this conversation and there are all of these people that normally think about global problems, thinking about this one as well, I think it's good. Another big thing, so the World Climate Research Program, which is sort of the father of the IPCC in the sense it's sort of coordinating role for a lot of the climate science going on, and it's very influential, has sort of declared that they want to play a big part in being sort of an impartial arbiter around the issues of should we do or how do we think about or what kind of research we do around climate intervention. So I think that's great. So these are all kind of small things, but I see the current moving a lot stronger right now, and there's a lot less hostility in thinking about and talking about this issue. And I think that this has to be a fundamental part even before we really talk about experiments, right? And then now the next step has to be, okay, but when we talk about experiment, what is it that we need to learn? And, for this in particular, I have to say that especially when it comes to sulfate in the stratosphere, I am a little bit skeptical about how much we need actual experiments in one sense. So I do think that before we actually go out and do this, we would need to do a lot of experiments. But right now, if the main issue is, are there things we're not thinking about? Are there impacts or effects that we are not seeing, not thinking, or maybe are unprepared to when it comes to, is this worth it thinking about at all? Or is there like a big stop sign that we're just ignoring? And my answer to that is that, well, but we do know that because there have been explosive volcanic eruptions. The climate has changed because of them. It has cooled, but the planet is still here. So there is a lot of that we can learn from a lot of the natural experiments going on. Then, of course, when we are going to be, and that has showed also how robust, in a way, our climate modeling has been in the last 20, 30 years. So when it comes to the kind of discussion that we need to be having right now, I am a bit skeptical about how much small-scale experiments could move the needle. Whereas I think that once we're going to go to the point where we've sort of gotten enough people on board that this is something that is really worth considering and we should move from the hypothetical, what if we did this, to, okay, how do we do this? That is the point where we need to start doing a lot more experiments and figuring out how to actually bring the stuff up in the stratosphere and thinking about how we're going to do it over the long terms. But before we do that, I actually think that a lot of the the work that we need to do is still very well grounded in a way, model word, which I don't think it's a bad word.
Dan, thank you so much for coming back for our periodic geoengineering check-in. We'll do another one the next time some industry accidentally stops our global experiment of spewing a bunch of sulfates into the atmosphere.
Okay, yeah, we'll see. But thanks for having me again. It'll be a pleasure to come again next year.
Dan Visioni is a climate scientist and an assistant professor at Cornell University's Department of Earth and Atmospheric Sciences. This show is a co-production of Postscript Media and Canary Media. You can head over to canarymedia.com for links to today's topics. Postscript is supported by Prelude Ventures, a venture capital firm that partners with entrepreneurs to address climate change across a range of sectors, including advanced energy, food and ag, transportation and logistics, advanced materials and manufacturing, and advanced computing. This episode was produced by Daniel Waldorf. Mixing by Roy Campanella and Sean Marquand. Theme song by Sean Marquand. I'm Shail Khan, and this is Catalyst.